Hi, everybody. Here's Catherine Jarmel from Probably Private. I'm here for another installation of learning about privacy engineering with the one and only Dr. Nigel Smart.
I'm Nigel Smart. I'm a cryptographer working on the privacy kind of technologies. I've been around doing this for far too long, and I'm currently chief academic officer, whatever that means, at a company called Zama.
Really cool work. And Zama's in the book. For close readers of the book, Zama is featured in chapter 8 and is doing some pretty cool work. So, Nigel, in your opinion, what is privacy engineering?
Privacy engineering is kind of like is creating solutions which protects privacy, and I put privacy in quotes because privacy has a very overloaded term of connotation in people's head. Because when you talk about privacy, people think about people's personal privacy. They talk about like, oh, kind of this personal identifiable information, but that's in some sense, privacy engineering is much wider than what we mean by privacy, because it's actually about any form of data that we don't want other people to learn about. So that could be your information, private information of an individual. It could be information of a company. It could just be analytics information that we might want to share, or it might be information that we kind of want to combine together, but we want to unlock the value of that information in a way which doesn't have any side effects that we can't quite foresee in the future. So in some sense, yeah, I think it's a kind of much broader term. Privacy engineering, in some sense, narrows our mental view of the world, whereas actually it's a much broader problem than just protecting people's privacy.
And this is why, especially in your field, this new term or terms like confidential computing. I don't know if you also have a definition of confidential computing you'd like to share.
Okay, so there's all sorts of computing things, okay, names. So computational computing is used by some people to mean methods of computing on data which do not reveal the data. And other people use the term confidential computing to mean specifically computing on data using trusted execution environments. And so there's a kind of confusing even about the term confidential computing. I kind of like the idea of using the term collaborative computing, because what it's about is actually everything is about combining data, being collaborative, and unlocking the value of data without actually revealing it to each other. It's basically unlocking the value of combined data. So it's collaborative computing is what I prefer.
Excellent. And I think you're touching a little bit on the aspects of trust and collaboration, and trust are key topics in your area of cryptography. Yeah. So maybe you can talk a little bit about what's the intersection of cryptography and privacy engineering, or let's even ask cryptography and collaborative computing.
Okay, so this idea of combining data from different sources and unlocking the value of data is actually a really old idea in cryptography. It goes back to the 1980s. Or maybe even before, yes, slightly before. And there are a bunch of technologies which enable this. So the classic technologies which enable people to combine data and unlock value. There are, as I've already mentioned, trusted execution environments, which are kind of like a hardware version of this. And then you have more mathematical ways of securing data, which do not rely on hardware or don't rely on the fact that you have to trust some specific manufacturer, say Intel or ARM or something. So these are zero-knowledge proofs, multi-party computation, and fully homomorphic encryption. And in some sense, the three of those kind of encapsulate the cryptographic methodologies to do collaborative computing, privacy engineering, or however you want to call it. And they're often kind of made to look like they're three different computing technologies, where actually in any major application that you can imagine, all three will be used together in some way. So in some sense, they're three complementary technologies which kind of combine together to form the whole of this collaborative computing ecosystem.
Which I think relates to like how you shape the use case. So one of the things that I try to point out in the book is like, each of these technologies can support different pieces of, even as you say, the same use case, or fit use cases better than one another. Has that also been your experience?
Yeah, I think really to illustrate that, it's really good to take a really simple example that everyone understands. So a classic example here is electronic voting. Okay, so everyone understands that. I want to vote for what's the best book on privacy engineering on the planet, say. Okay, so I have a bunch of votes for these books, and I look at one of them is for classmate's book, and one's for someone else's book, and so on, etc. And then people want to vote. Okay, so then when they vote, they want their vote to be private. Okay, so we've got a bit of privacy there. Okay, so I want the vote to be private, so I'm going to encrypt the vote. But I have to know that the vote is valid. I could be voting for, I don't know, the Stephen King book, and that's not a privacy engineering book, right? Okay, so what I now have to do is I have to prove that the vote is valid. So I have to provide with that encrypted vote a zero-knowledge proof that the vote is valid. So that's where zero-knowledge proofs come in. Tick one. Okay, now I've got the votes. Now I want to add the votes up. Now the votes are encryptions. So if I want to add the votes up, I have to perform some operation on the encryptions without decrypting them. So that's homomorphic encryption. And then when I've got the actual output of the vote, that's in encrypted form. So I have to decrypt it. Now, the way to decrypt it is what I would do is I would have a bunch of trusted parties, a bunch of election tally authorities, if you kind of think of it as like a political election. And these now execute a multi-party computation to decrypt the vote. So even in electronic voting, to correctness of vote is zero knowledge. The summing of the vote is fully homomorphic encryption. And the evaluation of the tally, getting the tally out of the homomorphic encryption, is an MPC computation. So we see there in a very, very simple application, all three are coming together to form a whole, which gives us the application in the end.
And the cool thing is it's like models trust in the real world around elections, right? Yeah. Like this is an online way of performing the same way that we go in, we make sure they know it's us, we make sure we punch the hole or the circle, and it's fully auditable as well.
Yeah. And the whole point is because the whole thing's auditable, you know that at each stage, everyone's evaluated everything correctly. So no one can cheat.
That's really cool. That's really, really cool. So I'd love to have the listeners or audience understand, they're probably intrigued by cryptography. How is it that you became interested in cryptography, and how did you become a cryptographer?
Okay, so I was originally a mathematician, so I was doing math, doing pure math, number theory type stuff. And then I realized you can make more money doing cryptography. So I was not a lecturer in math, and then I kind of decided, okay, I kind of want to actually see how this works in the real world. So I spent some time at Hewlett Packard Labs in the UK, and then I kind of set up a crypto group in Bristol, and then over time I moved to Belgium. This is Belgium behind me. This is our university in Belgium behind us. And then I've also kind of been involved in, advising big companies, banks and financial institutions on cryptography, and been involved in a bunch of startups over the years. So kind of half industry, half academia, which is kind of standard in cryptography. There's kind of like, very rarely do you find like a pure academic cryptographer. They're always kind of involved in stuff in the real world because there's so much applications of cryptography. It's just like, it's huge now, everything wants to use cryptography to make things secure.
And were you always interested in the particular fields of cryptography that you work in, or like what drew you to?
Changed over time. I was doing something to do with elliptic curve cryptography early on, which is very mathematical, but so this was in the 90s, and those days elliptic curve cryptography was just taking off. Now you use it in your browser. Your browser uses elliptic curve cryptography all the time. Every time you make a secure web connection, you're using the kind of stuff we helped develop in the 90s. So that kind of stuff is now like productized, boring kind of stuff. And then slowly, it's boring because it's used everywhere. It's standard, yeah.
I think it could be like you're welcome world.
Yeah, exactly. It's kind of like I don't know what else is boring. I don't know, like radio is boring, because it's been around for so long. Like, what else can you do with radio? And then kind of moved slowly into other areas. So, in particular, homomorphic encryption and multi-party. And so this really took off So mid-2000s, or really late 2000s-ish. Up until that point, everybody thought like multi-party computation, zero-knowledge proofs, homomorphic encryption, they were just theoretical rubbish. Like they would never, ever, ever be deployed. They were just too slow, too rubbish. And I remember sitting in a couple of talks at conferences, and people had done some really, really stupid, like small little demos. And the fact that you could do a small demo was like, oh my God, this is not complete rubbish anymore. This might actually be. You can imagine this is 20 years of people doing research into MPC, and no one had actually implemented anything because it's all just theoretical. And then some people did some things, and I went, oh, no, okay, maybe this is not so stupid after all. Maybe we can actually implement that. And so what we've seen since the late 2000s is a real massive change. So this is now, Google deployed this, Meta's deployed this, Amazon got people working on this. There are hundreds of startups. This is the foundation of how blockchain works. All these kind of different technologies. We've got the European Statistics Agency just launching something to do MPC for analyzing statistics, which is about the US Census Bureau doing stuff. So, banks are doing this for AML, anti-money laundering investigations. So this is huge. And the reason it's huge is because it's turned from a theoretical thing into a really practical thing because of three major changes. One, the cryptos got better because people suddenly realized actually you could implement this. People started looking at how can you actually make it go faster. So that's number one. So there's a lot more interest from researchers trying to make it go faster. So that's been one improvement. Another improvement is the computers got faster. So stuff that was impossible is now possible, which is kind of always useful. And the other thing is that networks have got faster and more reliable and more ubiquitous. So those three things together kind of combined and multiplier effects, and just taking something from just like, you could only do it on pen and paper for tiny, tiny examples, like multiplying two numbers together type examples in a lecture theater, through to we can compute on data sets and, evaluate neural networks, stuff like that. So that's been a massive change really over the last 15 to 20 years, maybe 15 years. And it just is accelerating. So that's really cool.
Yeah, I mean, it's amazing to see, and it's so heartening, I think, to see the large technology companies to invest in these technologies and to make them more widely available for people. And also that's very similar to what you're doing at Zama.
Yeah, so it's not just the big companies. There's a number of small companies doing specialist stuff. So we at Zama, we're specializing in homomorphic encryption, which is where you encrypt something, and then you can kind of manipulate the ciphertext and compute a function on the encrypted data without revealing the data. So this is kind of a nice technology. And we're kind of building, and what we kind of realized is, like I said earlier, it's not just the homomorphic encryption. You have to have the homomorphic encryption does the heavy lifting. But around that, you need to put zero-knowledge proofs, you need to put MPC protocols, you need to put other stuff. It's currently mid-July here. And next week, which is kind of like the week of like the 19th of July, we're kind of, Zara is going to be at the ECC conference in Paris. And we're going to actually be launching a testnet which allows you to evaluate smart contracts on encrypted data on blockchain. Probably, blockchain applications is the data is public. And you can know how many Bitcoin or how many Ethereum someone's got. You can evaluate these things. Whereas what we want to do is we want to encrypt the values. So you can actually evaluate the smart contracts in encrypted form. So that's so we've actually got something working, and a testnet will be launched next week at ECC in Paris. This is something you developers can go play with. We've had applications. If you go to the Hugging Face website, you can look at Zama's demonstration of image processing. Your browser encrypts an image using FHE. It goes up to the server. The server does some image processing in the encrypted form, then sees the image, sends the image back to you, and you decrypt it in your browser, and it goes, you've done this whatever processing you wanted. So there's this really cool stuff you can do. You can just, anyone can play with it.
And what's it like working with a large team of cryptographers every day at Zama?
Oh, that's kind of weird because, like, I don't know how many people have got at Zama now, but it's like a huge number of PhDs, and like almost anybody who is anybody is kind of in the specific area of FHE is kind of working at Zama. So we have like Pascal Payne is one of the founders, and he's like, donkey's years, he came up with this nice encryption scheme, the Payne encryption scheme, which is used in electronic voting. We've got a bunch of other people. So it's interesting because it's not just cryptographers, it's also people we have to have. If you could build product, you don't just need crypto. You need people who engineer the code. You also need compilers because you have to take, you're talking to a machine learning expert. They don't know only crypto, they understand machine learning. So kind of obviously. And so they will have like a Python way of processing, they'll use PyTorch to do their processing into their thing. So you want to kind of have, how do they use homomorphic encryption to encrypt data in a machine learning way using their tools? So we have to have a compilers which take kind of their kind of way of working and then translate it into stuff that the crypto can process. So we have compiler writers. And then the real big thing that's going to be coming maybe next year, 2024, is hardware acceleration. So hardware acceleration, or specifically of homomorphic encryption, is going to give us 100 to 1,000-fold speed up. So currently, FHE computations, everyone thinks is about 10,000 times slower than doing stuff in the tree. So if your application took 1 day, it's now going to take 10,000 days, which is kind of a bit of a problem, yeah? But there is hardware in demo at the moment. Some researchers at the University of Leuven have done this. And there's also a number of companies working on hardware accelerations. And a lot of these accelerators are going to come online in 2024. And the early indications are from the FPGA demos or the other demos that have been around, that they should be 100 to 1,000 times faster. So you'll see something that would take, say, if your algorithm took 1 hour to run on clear day, 10,000 hours to run on FHE. But this is going to come down to 10 hours. Mm-hmm. You suddenly see that there's suddenly, if you're going to wait 1 hour for something to run, waiting 10 hours isn't that, much extra, especially if you're kind of processing data, the private data. So this is going to bring so many new applications into scope, and it's going to be a real game changer. So we're going to really see, we're seeing applications now. I've already mentioned stuff, Facebook, Meta, Google, Facebook, Amazon, US government statistics, European statistics agency, and banks, etc. But now this is going to accelerate even more, because once you get hardware on board, people can find hardware that makes things 100 to 1,000 times faster, suddenly the number of applications is going to skyrocket.
Absolutely. Absolutely. And so do you think that will Zama be hiring FPGA developers as well? Or are you going to work in?
We already have FPGA developers. We already have people working with the hardware vendors. So we
awesome.
have relationships with all of the major.
Awesome.
So, everybody's working together on this in a kind of coopetition, like
collaborative product development.
Yeah. Collaborative and coopetition. So it's competitive, but also cooperation at the same time. Yeah.
Yeah, I mean, it's really like the field is truly shifting right now. I'm not sure if it's obvious to everybody, but your work obviously has created a lot of the ability for things to shift so quickly.
Yeah, I mean, so you think about, we've been talking about FHE, so if you think about MPC, this has been, if you're using blockchain, there are a huge number of MPC companies now in the blockchain space. I founded a company called Unbound Security, which was sold to Coinbase, was it 2 years ago or a year and a half ago, something like that. So, if you use the Coinbase wallet, you are actually using MPC. Our companies are doing the same thing. There's Fireblocks is doing something. There's a Paris company called Defense. There's Blockdaemon. There's, endless. Everything in the chain space uses MPC all the time. Zero knowledge proofs are kind of becoming more and more deployed. If you want to use blockchain, you want to use level 2, level 3 blockchain, you're using zero knowledge proofs. If you want to use, there's all sorts of applications of zero knowledge proofs coming. So we've been involved in the US government with Leuven University, who were involved in a project US government where they were thinking of how could you prove to someone that you'd found a bug in their code. So here's some code, and I want you to pay me for having found the bug. Mm-hmm. I'm not going to reveal the bug to you until you've paid me, but I have to convince you there's a bug, right? So you can actually do this. So we actually showed, there's a famous bug in SSL called Heartbleed, and we could prove to someone that Heartbleed was in the code without actually revealing the thing. So it was a kind of like, this was a genuine bug in code, in a large piece of code, and you could demonstrate it in with standard zero knowledge proofs techniques these days. So all of these technologies are rapidly scaling up and rapidly finding applications in all sorts of weird ways across the ecosystem.
it's massively exciting as somebody who must be there kind of at the front line. So to kind of give people a perspective, what's your perspective? The field of collaborative computing, the field of cryptography or applied cryptography is really what we're talking about, these kind of methods that have been around for decades now, but are scaling into production systems. How do you expect these fields to grow, and how will they change as they grow?
That's a kind of a big question. I think they're going to accelerate. I'm thinking we're seeing, like I said, like what we've seen over the last 15 years is better networks, better computers, better maths coming together. I think this is just going to accelerate more and more, especially if people suddenly see that there's more and more opportunities here. There's going to be more ideas coming in. We see specialized hardware, which is kind of what I've just been talking about. You might find specialized networks, special ways of communicating. So these things are going to accelerate these combined factors. And then what we're going to actually see, which is the really interesting thing. So we have these three internal things: computing, network, and math. But now what we're going to see is applications coming on board. And applications are going to drive even other innovation, because once an application comes on board, what you see things that people haven't thought of before. Oh, we need to worry about this. Oh, we don't need to worry about this, because actually the application means that we don't actually need to worry about something we can worry about. So we can actually get rid of some stuff and make it go faster. So I think we're going to see, once the applications come on board and there's more ubiquitous applications, we'll see even greater acceleration. And you can kind of see this in normal crypto, just crypto for communicating. Yeah. So we go back 15 years, everyone was using SSL, which was a bit rubbish. SSL. We had email, and email encryption never works, right? So email encryption doesn't work. Really, really bad. Anyone who's tried to encrypt an email, forget it. It's really horrible. It just doesn't work. And that's because email is built in a world where not everybody's online all the time. Is that you send an email to someone, and then 2 or 3 hours, or depending if they're lazy, a week later they download it and they read it. They're not actually online at the same time. And so the security properties you get and the usability is not really very good. Whereas what we see now, and what is really seen accelerating, is things like Signal and WhatsApp, where everybody's online all the time. We have very, very simple applications, and the security given by WhatsApp and Signal to message security is now hugely improved over anything we can get on email encryption, because everybody's online. AIs, the application interfaces are really, really easy, and everybody, even your grandmother, can send encrypted messages that no one can intercept using WhatsApp and Signal. So it's kind of, we're seeing this huge improvement, and some of that's come about because people are going, oh, well, okay, email's hard. But hold on, we've got this other thing, this other application that's actually sending messages. We could do this. And then actually that means things become a lot easier, because that application actually means a lot of the problems that you have with email encryption just disappear, because the application itself removes those problems, so you can actually get better security, better user interface, etc. I think we're going to see a lot of that in this collaborative computing space as well. And also we'll see unlocking of value. So again, we go back to the past. You can map the internet. Okay, so I have a story. Someone I know was involved in a very early discussion on security of the internet. And so he was called into a room with a bunch of what he called spotty teenagers. And these spotty teenagers said, well, how can we do security on the internet? How can we send messages encrypted on the internet? This was before SSL was around. And he went, well, why do you want to do this? Well, someone can send credit card details. He went, you're not allowed to send credit card details on the internet, because internet is not allowed to be used for commercial purposes, which was true in those days, yeah? But these people were kind of thinking, okay, we could use the internet for commercial purposes. And they were just thinking about sending things around. But now what we have is a whole new industry of e-commerce that didn't exist before. Different ways of doing business because we have the internet. Now, if you imagine you've got this world where we have collaborative computing, where organizations, individuals can share data in a way which protects their data, but which allows you to unlock value from that data, you now have new businesses. You now have new ways of things that we haven't even thought of doing that you can do. Really classic example that people have actually thought of is, even if you just think about it, I'm sitting here in a nice, lovely leafy estate in Nervin, and actually some people got solar panels, some people haven't got solar panels, but actually we could share our electricity in a way where we can protect, what electricity we're actually consuming, but we could actually kind of unlock the value of the of the electricity consumption and production within a locality in a way which kind of unlocks value, which means that spare capacity is used, that we move stuff around the grid more effectively. But the reason why we're not kind of doing that at the moment is because a lot of that data is actually confidential. So if we can keep the confidentiality but still unlock the data, we can get unlock huge value. And that's like a business that no one has thought about before. So, well, people have, but the businesses like that, no one's thought about before.
Yeah, and I think as you alluded to, it also replaces maybe some older and less useful ways of doing this, where we have to trust that we send all of the data of our energy use to some sort of central authority, and that authority will use it responsibly. And I think it enables massively different ways of thinking about data sharing and data use across communities. Yeah.
So it's kind of really exciting times coming in from the applications as well. So hopefully some people on this podcast could watch this and they'll go like, hey, I've got an application. Great. It's really good. That's good. Let's go out, form a company and make it happen.
Awesome. Awesome. Nigel, thank you so much for sharing all of your knowledge and for your many decades of supporting this work and bringing it forward and bringing the future of collaborative computing that I know I'm excited about, that I think a lot of people are excited about. How do people follow your work? How do people catch up with everything you're doing and thinking?
Okay, so you can follow me on Twitter. Smart Cryptology is the handle. You can, just follow Zama, there's all sorts of organizations you can follow. There's NPC Alliance, there's the FHE.org for homomorphic encryption, and there's one for zero knowledge.
We'll put all the links in the description on YouTube and so forth, so you can check there. Thank you again, Nigel, for your time, for your work, for your expertise, and keep on with the collaborative computing.
Thanks very much. Cheers.